To start, photophoresis is a phenomenon where a particle spinning in a gas or liquid begins to migrate when illuminated because of an imbalance in the momentum transfer between the gas particles and the suspended object due to a heat gradient across the suspended object. To get a grasp of what this means, let's consider a spherical dust grain suspended in a gas with infinite volume. If we apply a light source in the positive x direction, then the right side particle will heat up. Now, assuming that all the gas particles that collide with the surface of the dust grain equilibrate with the surface temperature of the grain before being ejected again, then the gas particles come into contact with the hotter side of the dust grain, leaving the surface of the grain with a greater velocity than those that collide with the cooler side. From a momentum standpoint, we can let the initial momentum of the dust grain, P0, and the momentum of the incoming gas molecules, Pn, equal the final momentum of the dust grain, P, and the momentum of the outgoing gas particles, P out. Now we can rearrange this expression using impulse to get an expression for the photophoretic force. Now, to evaluate the photophoretic force, we need to find expressions for the momentum of the incoming and outgoing gas particles. Let's start by considering the momentum of a single gas particle. Though when considering the momentum transfer between the gas and the dust grain, we are only interested in the velocity component normal to the surface of the grain. So we will multiply our expression by cosine theta, where theta is the angle between the velocity vector and the plane tangent to the surface of the dust grain. If we sum up the momentum of the incoming gas particles, we get an expression for the total incoming momentum. But sadly, this would require enormous amounts of computing power, so we will need to use a different method. But before I continue, I need to cover some spherical geometry. First, let's take a sphere and cut up into wedges about the x-axis so that the angle phi is the radial distance about the x-axis from the positive z-axis to any point of the sphere, and range from 0 to 2 pi. Next, let's cut up the sphere parallel to the yz plane like a loaf of bread, where theta is the radial distance about the z-axis from the positive x-axis to any point on the sphere, and range from 0 to pi. When we put these two angles together, it creates a grid we can use to identify any point on the sphere, and now we can use 2 theta and 2 phi values to create an area on the sphere. If we take an infinitesimal change in phi, d phi, and an infinitesimal change in theta, d theta, create an infinitesimal area component with area r squared sine theta d phi, where r is the radius of the sphere. Now back to photophoresis, let's define the area of the dust grain as the integral of all of the area components. So this introduces a new concept, multiple integrations. To understand how to integrate this expression, let's first consider taking a single integral. Looking at the function f of x, the integral is just the area under the curve. To find this, we divide the area up into infinitely many rectangles with infinitesimal width, and then sum up the areas. Now considering the function f of x of z, the integral of this function is the volume underneath the curve. To find this, we will divide the volume into infinitely many rectangular prisms with infinitesimal thickness, and then sum up all those volumes. One important thing to notice is that for each prism, only the z value changes and the x value is constant. This allows us to treat the variables we are not integrating across as constants. Thus, for our equation, for the surface area of the dust grain, we can separate the integrals. We can also put r squared as this constant. Now we're left with 2 easy integrals, and then where we evaluate, we get 4 pi r squared, which is just the surface area of a sphere. Given that we have an expression for an area component, let's consider the incoming momentum to a single point on the dust grain. Let's start with an expression for the sum of the momentum of all of the incoming gas particles. But as I already stated, this is not a feasible solution. But upon closer inspection of the formula, you may realize it can be expressed as the momentum of a single gas particle times the number of gas particles striking the surface per unit area, where v cosine theta is the average component of the gas particle's velocity normal to the surface of the dust grain. Now if you let n equal the gas flux I, normal to the surface of the grain, which is the number of gas particles that pass through a unit area per unit time multiplied by the area of the point which we found earlier. Then we can get an expression that we can compute. Now we just have to integrate over the surface of the dust grain. But given that we know that there is a radial symmetry about the x-axis, we only have to consider the components of the momentum parallel to the x-axis. Thus we will integrate our expression for the incoming momentum to a point on the sphere times cosine theta from 0 to 2 pi and from 0 to pi. Again, we will separate our variables and bring out constants. Let's integrate cosine theta, sine theta, d theta first. To do this, we need to make a u substitution, so that u equal sine theta and du equal cosine theta d theta. Plug these back in and integrate. This gives us a value of 0, which means the net incoming momentum is 0, which makes sense, because if the gas is uniform, then the flux and thus momentum to each point on the dust grain is the same. Now that we know the net incoming momentum, the next step is to find the outgoing momentum. Let's start with the equation for the incoming momentum to a point and make some adjustments. We can assume that the outgoing gas flux is the same as the incoming gas flux. We can also assume that the mass of the gas particle doesn't change. We can still use the same area component. Thus, the only thing that will change is the velocity of the outgoing particles. For a single gas particle, the thermal energy equals its kinetic energy. This results in the following expression, where K is a constant and T is the temperature of a gas particle. Assuming that the temperature of an outgoing gas particle is equal to the surface temperature of the dust grain, we can plug in F of theta, which is a function of the dust grain surface temperature as related to theta. We can now solve for the velocity of a gas particle and plug back into our equation for the outgoing momentum at a point on the dust grain. Next, we need to integrate over the surface of the sphere from 0 to pi and from 0 to 2 pi. Then we can separate out our variables and pull out constants, then integrate phi. But before we continue, let's first find an expression for the gas flux to a point. To start, let's consider a point on the surface of the sphere. Because the gas particles can come from any angle, we can't just multiply the number density of the gas by its velocity. But we can take advantage of the gas being uniform, which means that the gas flux of any flat surface area is constant. So let's create an imaginary spherical surface around the sphere and divide up into infinite area components so that any individual area component is essentially flat. Now let the radius of the sphere equal the gas velocity, which gives us the expression for the infinitesimal area component. By multiplying this by the number density of the gas, we get an expression for the flux to the area component. But again, we only want the flux normal to the surface of the grain. So let's multiply our expression by v cosine theta. So there's still one more problem with our expression. The velocity of the gas is actually not constant. It follows a Maxwellian velocity distribution defined by the function f of v, where f of v is the relative concentration of velocity v and the integral of f of v is 1 when integrated from 0 to infinity, and the mass is m of a gas particle. K is a constant, T is the temperature of the gas, and V is the velocity of a gas particle. To account for this, we will find the gas flux for each velocity by multiplying our expression by f of v dv. Then to find the total gas flux, we will integrate this new expression from 0 to infinity. Now to find the total flux for the point, we will integrate the expression for the flux to an area component from 0 to 2 pi for phi. But because the dust grain blocks the gas flux from underneath the tangent line to the surface of the dust grain, we will only integrate theta from 0 to pi halves. Like before, we will separate out the integrals and pull out constants. From before, we know that the integral of 0 to 2 pi d phi is 2 pi. We also know that the antiderivative of cosine theta sine theta d theta from before is sine theta squared over 2, which we will evaluate from 0 to pi halves. This yields 1 half. We can plug this back in, and now we need to integrate over velocity. To do this, we first need to make a u substitution, so that u equal v squared and du equal 2v dv. When we plug this back in, it still leaves a v squared. But because v squared equals u, we can just plug in u for v squared. Now to integrate this, we need to do an integration by parts. Integration by parts states that the integral of u dv is equal to uv minus the integral of v du. So let's let u equal u and dv equal e to the negative mu over 2kt du. Now before we can perform integration by parts, we need to find v and du. Du is easy, it's just du. To find v, we need to do just a little bit more work. If you remember, the derivative of e to the n is the derivative of n times e to the n. So the integral of e to the n is 1 over the derivative of n times e to the n. We can apply this to dv and plug back into the integration by parts formula. Because negative 2kt over m is a constant, we can pull it out and then integrate. Now we can plug back in v squared and then evaluate. After simplifying, we can plug this back into our expression for the flux. Now we can simplify again and plug back into the expression for the outgoing momentum and simplify. And finally, we can plug this back into our expression for the photophoretic force. This gives us the equation for the photophoretic force on a spherical dust grain with a temperature gradient T of theta.